All right, subscribers, welcome back to another episode of Science with Surback. Today we're going to look at sections 4.3, and this deals with how atoms differ. Now, before we get into the details of these notes, there is a few objectives that I would like to outline. Objective number 1, explain the role of atomic number in determining the identity of an atom. Objective 2, define an isotope and explain why atomic masses are not whole numbers. And objective number 3, calculate the number of electrons, protons, and neutrons in an atom given its mass number and atomic number. So we start out here with what the atomic number is. And the atomic number is defined as the number of protons in the nucleus. And you'll see this is found by the gentleman by the name of Henry Moseley. He'll come into play when we start talking about the periodic table a little bit more in depth and in detail. But with this atomic number, which is equal to the number of protons, it's going to determine where that element is in the periodic table. So I'm going to grab a periodic table, and you should have one handy as well. But as you can see, as we move left to right, the atomic number gets larger. And I'm going to make a note here that this atomic number is this whole number, okay? So the atomic number is the whole number. Now, I also want to make a note here that the atomic number is equal to the number of protons in that particular atom. Now, if we change the number of protons, we change the element that we're working with. So again, what I'm trying to say here is that the element has a unique number of protons. If that number is changed, we now change the element that we're working with. And I should also point out too that these highlighted words should correlate to the blanks that you need to fill in on your notes. You also need to include anything that I write down extra on these notes. Now, for the next few chapters, we are going to be dealing with neutral atoms, and these neutral atoms mean that there's going to be equal protons and electrons. We want the positive charge to cancel out the negative charge, okay? So you can see lithium has an atomic number of 3, and this means that we have 3 protons and 3 electrons. So keep that periodic table handy, and let's go over some examples in determining the atomic number of protons and electrons. So we start out here with this chart, and we have a couple of different things that we need to fill out. One is the element symbol, 2 is the atomic number, and 3 is the protons, and lastly is the number of electrons. We start out here with this top row, and we find that we have PB here, and we look for PB on the periodic table, and we find that it is element number 82. Now, 82 is listed as the atomic number, and the atomic number is equal to the number of protons. So the number of protons here for PB or lead is 82. Now, because all atoms are neutral, that means we have equal number of electrons and protons. So this means that because these atoms are neutral, that lead is going to have 82 electrons as well. Now we get something that is only giving us 8 protons. Well, remember, protons equal the atomic number. So, because they are equal, I'm going to put an 8 in this box here. Now, once you have the atomic number, we can look this up on the periodic table. And so we find atomic number 8, and the symbol for this element is O for oxygen. So we would fill in O for oxygen. Now, once again, the number of protons is equal to the number of electrons, so we put 8 as well. All right, so we work backwards here on this last row. We have 30 electrons, and in a neutral atom, electrons is equal to protons, so that means we have 30 protons. More importantly here, the number of protons determines that atomic number, so that means we have 30 as our atomic number. We look for 30 on the periodic table, and we find this element zinc. So the element zinc has the symbol Zn, okay? So the main thing with this is the atomic number can be correlated to what element is or that we are dealing with on the periodic table. All right, let's keep moving on here and going through this process. Now, you may have noticed that on the periodic table, there is another element, and we've talked about this element here. It's the atomic mass, and it's actually the average atomic mass, which we'll get into those details a little bit later. But the reason that we have that decimal number is because we have isotopes. Now, isotopes deal with elements that have the same number of protons. So we're dealing with the same element, but they have different number of neutrons. What that does is that varies the atomic mass of each individual isotope. So let's take example potassium. In potassium, there are 3 naturally occurring isotopes. Now, every potassium isotope is going to have 19 protons. Remember, if we change the number of protons, we change the element that we are dealing with. However, each of these 3 isotopes is going to contain different number of neutrons. Now, the next thing you may be wondering is, well, how do they get that decimal number? Well, they take the isotope mass and they take the relative abundance. So these 3 isotopes are not equal in nature. They have different percent abundance or different percent that is in the universe. This number and the atomic mass is factored in for each isotope to give us that average we see on the periodic table. Now, if we do this problem, we could find that the value for K potassium would have this decimal number of 39.0983. Again, just using the percent abundance and using our atomic mass for each isotope will allow us to get to that point. Now, I mentioned some things that we need to go over before we get any further, and one of which is the mass number. So the mass number is defined as the sum of protons and neutrons in the nucleus. And it has a formula that the mass number is equal to the number of protons and the number of neutrons. Now, I want you to write this down next to the mass number formula. So the mass number, I'm just going to use the hashtag symbol, mass number is equal to number of protons plus the number of neutrons. And that formula is going to be very helpful going forward here. Okay, so here we go. What we can do is we have to determine, because there's multiple isotopes of each element, we have to determine what isotope that we're working with. So there's 2 different ways we can write that isotope notation. Number 1, we can write out the name of the element followed by the atomic mass. So again, this is the name, and this is the atomic mass, or what we would call the mass number. Now, the other way that we can express this is the element symbol notation. Now, 3 things are required for the element symbol notation. One of which is the element symbol. The second thing is the mass number, which again, we're still dealing with that same isotope, so it's still potassium 39. And then the third thing is your atomic number, which remember, the atomic number is equal to the number of protons. This is very helpful in identifying the number of neutrons. In fact, both of these notations can be used to identify the number of neutrons. So let's go over, let's use this formula, and let's use these symbol notations to be able to go over our next set of problems. All right, so here it says in our example, a chemistry lab has analyzed the composition of isotopes of several elements. The composition data is given in the table below, in this table right here. The data for one of neon's 3 isotopes is given in this table. We want to determine the number of protons, electrons, and neutrons in this isotope of just neon. We also want to name the isotope and give its symbol. Okay, so we want to use both of those isotope notations that we just went over in notes. So we are dealing with neon, so I'm going to highlight neon here so that way we know what we are dealing with. Okay, so with our isotope notation, there are 2 different isotope notations, one of which we called the element name form. So I'm going to write this down, element name form. And in this element name form, we start out by writing the element name. And it is neon, it's given here, neon. And then we follow it by the mass number, okay? So the mass number, real simple here, is 22, okay? Well, that was easy. And then we have the element symbol form for writing an isotope. And so what we do with the element symbol form is, number 1, we need to look up the symbol for neon, which is Ne. So we start out by writing Ne, and then on top, in the upper upper left-hand corner, we write the mass number. The mass number of neon is given at 22. So we write 22. And then below, we write the number of protons or the atomic number. Again, the atomic number 10 here for neon, is equal to the number of protons. Okay, so we have done the last part of this problem, name the isotope and give both of those isotope notations. However, we have not explicitly gone over the number of protons, neutrons, and electrons in this particular element. So what we need to do, the next part of the problem here, is we're going to break out that formula. The mass number is equal to the number of protons plus the number of neutrons. Okay, so we're just going to plug our numbers in. The mass number is nice because it's given. It's given at 22. So what I'm going to do here is I'm going to put 22 in place for that mass number. Now the number of protons, it does not explicitly say what the number of protons is, but remember the atomic number 10, which it's listed here in the chart, and it's found on the periodic table, is unique to each element, and the number or the atomic number is equal to the number of protons. So I'm going to put that here, equals number of protons. Okay, so that means because we have an atomic number of 10, we have 10 protons. Now, we do not get the number of neutrons given to us. So our number of neutrons is what we are actually going to be solving for. Now, what we need to do here is we need to subtract 10 from both sides. I'm going to subtract 10 from both sides. 22 minus 10. Hopefully you can see that in your head, but that's 12. See, 22 minus 10 is 12. Okay? So 12 equals our number of neutrons. We just got done saying that 10 is both the atomic number, which is equal to the number of protons. So 10 is our number of protons. And remember, we are dealing with neutral atoms. Unless I tell you differently, we're going to be dealing with neutral atoms from here to the given future. So the number of protons is equal to the number of electrons, which means we have 10 as our number of electrons. All right, so now we've answered that question. We have the element name, element symbol form of our isotope, and we've answered how many protons, neutrons, and electron are in this particular isotope of neon. All right, so moving on here, we have to get to what these numbers actually mean. Notice how I did not put any unit associated with these particular numbers. So we move on here and we get into this atomic mass unit. That should technically be the unit that accompanies each of those numbers that we have gone over. And this is, again, a unit value that's associated with relatively the mass of one proton or one neutron. Notice how the electron is very, very small, so we don't include that in it. But specifically, the atomic mass unit is 1/12 the mass of a carbon-12 atom. So essentially what they did is they took carbon-12, has an atomic mass of 12, and they said, hey, let's divide it into 12 equal parts, because there should be 12 parts in the nucleus, and that is the mass of one atomic unit. Now, for us, this is the most important here. The mass of one AMU, or atomic mass unit, is equal to the mass of a proton or mass of the neutron. So I want you to notice here, these values here in this table, you can see it a lot better on your chart, but these numbers for a proton and neutron are very close to 1. Yes, they have some decimals past it, but they're very close to 1. Over here, notice how the electron has many, many zeros past that first decimal point. So the mass of the electron is very, very small and doesn't really need to be included. 1 AMU is equal or relatively equal to mass of one proton or neutron. Okay? Now, let's go over the atomic mass. And before I transition to this next page of notes, notice here for the atomic mass. Remember, the atomic mass is this decimal number that is seen on our periodic table. Okay? So the atomic mass is normally a decimal number. Now, you may be wondering, well, how do they get that decimal number if we just went over the atomic mass is a whole number? We just went over several problems where we showed the atomic mass or the mass number is equal to the whole number. Well, lo and behold, we have a way that we can find the actual atomic mass or the average atomic mass that is seen on the periodic table. What we have to factor in is two things. One, isotopes have different mass numbers and they have different percent abundances. So what happens here? For example, chlorine. If we find chlorine on the periodic table, it is listed as 35.45 AMUs as this atomic mass average, okay? So what happens is they take the relative abundance of everything, of the two isotopes, and they average it in a unique way, which we'll learn here, and they get that number that is seen on the periodic table, okay? So what we have to do here is this. to find out what the average atomic mass is, we need to first find out the two isotopes, and we need to figure out both the mass of the very specific mass of that isotope and the percent abundance. We need to multiply the atomic mass and the percent abundance of each isotope. But I want to add in a step here, and that is you need to convert this percent abundance to decimal form. Okay, that is very important. Then you can multiply this. You're going to get multiple values. You then add these values together, and you should be able to have that average atomic mass for one particular element. Okay, I know these steps are a little bit broad, but hopefully it's a little bit more clear in our particular example. So let's go over the example. It'll be the final thing that we do in these notes. All right, so here we go. All right, we have this particular example. It says, given this data in this table below, calculate the atomic mass and identify what element it is. Okay, so we start out with this. We're going to start out with the percent abundance. So what we're going to do is this isotope, we don't know its element, so we just write down X6. And the first thing that we do is we take the percent abundance and we make it a decimal form. So I'm going to take 7.5%, and the way we make it a decimal form is we divide that number by 100. Okay? So what we do here is we take 7.5 and we divide by 100. Well, we're going to write down this decimal number. So 7.5% is equal to 0.075. Now, very important here, because we multiply by the exact atomic mass that is given. And it has to be very particular. It is this atomic mass. So we multiply by 6.015, and I'm going to plug that into my calculator. So I'm going to take 0.075 times 6.015. I'm going to press enter. Now, I'm going to use 4 decimals in this case, and so I'm going to write down 0.04511. And the unit for that is equal to the unit for the mass. So I'm going to write down AMU. Now, we're going to do the same thing for the other isotope of this element. Again, we start out here with X. We take the percent, and we have to take it out of percent form, and we have to divide by 100 to take it out of percent form. So we put 92.5 divided by 100, and we put 0.925. So we have 0.925. We multiply it by the exact atomic mass, which in this case, for this particular isotope, is 7.016. This is equal, let me plug it in my calculator, 0.925 times 7.016. This is equal, again, 4 decimals, 6.4898. And again, the unit is that atomic mass unit that we just went over. Now, the last step here is adding these numbers that we've just spent the time going over and getting our atomic mass. So I'm going to put 0.04511 plus 6.4898, the numbers we just went over. And I get a value of 6.941. Okay, I'm rounding here to 3 decimals. Okay, so 6.941 AMU. U. Okay, now we're not quite done because we've just identified the average atomic mass. Now, according to this problem, this should be an exact element on the periodic table. So I'm going to scroll over and I'm going to find, oh, hey, look, the element that has an atomic mass of 6.941 is lithium. Okay, so element X is lithium. All right. Or if we want to put the name, we can put lithium. Okay, so we went over a lot. We went over a lot of math calculations in this particular section of notes. Make sure you take your time and identify exactly what a problem wants. As always, I hope you've enjoyed this episode, and if you haven't done so already, make sure you subscribe.